We count on science to give us clear, objective answers. But what happens when the very tools researchers use have, well, a mind of their own? Today, we're going to hunt for a ghost in the statistical machine and see how a supposedly good neighbor can end up putting a thumb right on the scales of truth. So let's start with a classic question, one I'm sure we've all thought about. Does being happy at your job actually make you better at it? It feels like it should be true, right? A happy worker is a productive worker. It's a kind of idea that social scientists just love to sink their teeth into. And to get to the bottom of a question like that, researchers use some seriously powerful tools, like structural equation modeling. Now, don't worry about the name, just think of it as a way to create a statistical map. It draws lines between big, complex ideas to see if one thing, like happiness, truly leads to another, like performance. But here's where the plot thickens. What if that mapping tool, the one that's supposed to be totally neutral, has a secret little instruction, a built-in assumption that gently nudges the results toward what the researcher was hoping to find in the first place? Yeah, this is where the machine might not be as objective as we think. Okay, so to really get why this is a problem, we need to quickly wrap our heads around one key concept that researchers deal with all the time. And that concept is called a latent variable. It sounds complicated, but it's not. Look, you can't just stick a thermometer in someone and measure their job satisfaction. It's an invisible idea. So, instead, researchers ask a bunch of related questions. Are you fulfilled by your work? Do you enjoy your team? And they bundle the answers into a single score that represents that big, fuzzy idea. All right, so we're trying to connect one of these latent variables, satisfaction, to another one, performance. And to do that, some of these statistical programs make a very specific and, as it turns out, very influential assumption. Let's meet our main character, the good neighbor. The good neighbor assumption, we'll call it the GNA, is basically an instruction that tells the computer, hey, listen up, these two concepts are supposed to be related. So when you're doing your calculations, do me a favor and make them look like, well, good neighbors. Make them seem as connected as you possibly can. It's a little nudge, meant to be helpful. And hey, we're not just making that name up. It comes directly from the folks who created this method back in the 90s. They literally wanted the algorithm to create variables that were good predictors for what came next and were well predicted by what came before. The whole point was to find the strongest possible connections. But that goal has some unintended consequences. So this is the really critical difference. On one side, you've got a method called PLS regression. Think of it as a neutral observer. It calculates the scores for satisfaction and performance completely on their own independently. Then, after the fact, it checks to see if they're related. But on the other side, you have modes A and B, which use that good neighbor assumption. With them, the researcher's hypothesis, the idea that these two things should be connected, is baked in from the very start, influencing how the scores are even calculated. So what really happens when this good neighbor starts meddling? Let's look at a real study to see these side effects in action. Researchers set up this exact model. They took data from almost 200 professionals and asked that simple question: does job satisfaction predict job performance? And to see what was going on under the hood, they ran the analysis with all three methods. And whoa, check out the results. Look at that strength column. As we go from the neutral method, PLSR, down to modes A and B, the relationship looks stronger and stronger, right? It goes from 0.433 up to 0.455. But now, look at the next column, collinearity. That's basically a measure of statistical static or noise. It also goes up. So the good neighbor isn't just finding a stronger result. It's artificially inflating it while pumping more noise into the system. And this chart just paints the perfect picture. The neutral method, PLSR, is down there on the bottom left. But when we switch on the good neighbor with modes A and B, the result gets shoved up and to the right. It looks like a stronger connection, sure, but it comes at the cost of more statistical noise. It's the literal definition of putting a thumb on the scale. But hang on, it gets weirder. A lot weirder. Inflating a result is one thing. But what happens when this helpful neighbor doesn't just nudge the data, it actually starts to break the very measurements it's supposed to be using? This leads us to a truly bizarre statistical gremlin called Simpson's paradox. In this situation, it means that one of the survey items you're using to measure, say, job performance, suddenly starts working against it. Instead of adding to the overall picture of good performance, it starts subtracting from it. It's totally backwards. Get a load of this number. When they used the most aggressive good neighbor method, mode B, one of the performance indicators wound up with a final score of negative 0.099. This is just fundamentally wrong. An indicator designed to spot high performance was actually lowering an employee's overall performance score. The algorithm twisted the data so hard to make the variables good neighbors that it completely broke its own internal logic. So, why on earth does this happen? Why does this well-meaning assumption create so much chaos? Well, the answer lies in the true shape of the data itself. At the end of the day, the good neighbor assumption is really just a clumsy attempt to deal with the fact that relationships in the real world are messy. They're almost never perfect straight lines. But instead of actually finding the real complex shape, the GNA just tries to brute force the data points closer together, and that's what causes all these strange side effects. And when the researchers actually plotted the data from their studies, well, there it is. The real cause becomes crystal clear. The relationship isn't a straight line at all. It's a curve. In the first study, performance goes up with satisfaction for a while, but then it starts to level off. The good neighbor can't see that curve. It only knows how to jam a straight line through the data, and that's what creates the whole problem. So what's the fix? Simple. Use a tool that's actually designed to find curves. When the team reran the analysis with a nonlinear method, that's the PLS-SEM here, they got a result that was even stronger than what the good neighbor produced. But, and this is the key part, look at the VIF score. It stayed nice and low. They found the real, more powerful relationship without adding any of that statistical noise or breaking their own measurements. Which brings us to the biggest takeaway of all. It's not that the good neighbor is always evil, but it means that scientists absolutely have to know what their tools are doing under the hood, and then choose the right one for the job at hand. So, think of it this way. If your goal is to confirm a theory, you have a hypothesis and you want the cleanest, most unbiased test you can get, you use the neutral method, PLS regression. But if you're just exploring a data set and you want a tool that's extra sensitive to finding even the tiniest hint of a connection, and you're okay with a higher risk of a false alarm, then maybe, just maybe, the good neighbor methods could be useful. Ultimately, what this shows us is that buried deep inside the powerful algorithms that drive so much of modern science, there are choices. Assumptions are being made. So the next time you see a headline about a new scientific finding, it's worth asking yourself, was the tool they used just a neutral observer, or was it trying to be a good neighbor? Because that one tiny choice can change everything.